Okay, I'm walking you through my digital systems number two. So in here, inside the second week, we covered a lot more materials than we did in the first week. But I guess it was slightly easier because the first week felt like I have no idea what's going on. The second week, it felt like, okay, yeah, it's just some more new information. So here we have just basically talking about the composition of the microbit architecture. So what we have is we have the microbit, and then on top of that we have the Nordic chip, and then on top of that we use the um, ARM thing. So the idea is that we have the CPU. The CPU is ARM Cortex M0. The architecture has standard registers and data path. It has some base control, so it uses some instruction set, and it has interrupt controller, so it handles external events and signals. And then outside of that, we have the CPU processor Nordic. The Nordic is responsible for memory specifications such as RAM and then flash ROM. So our RAM is we have 16 kilobytes that's used for temporary data and stack. And then we have 256 kilobytes for storing code permanently. So we definitely have a lot more ROM than RAM because it's cheaper, obviously. There's also part of the Nordic, there's the peripherals, which are basically auxiliary devices used to control physical components, such as the LED lights, the also we have something known as interfaces, which are basically protocols that processor uses to communicate with the peripherals. And then there's three things that we kind of have to know. GPIO, I2C, and UART. The GPIO stands for General Purpose Input Output. So it's the interface for LED buttons. So then anything that's on and off, like those things that have states. I2C is inter-integrated circuit. What that means is that it's for sensors like accelerometer and compass. I haven't gotten to use that yet, but I definitely use GPIO, not yet for I2C. I use this one. This one is for Universal Asynchronous Receiver Transmitter. That's where the UART comes from. And it's responsible for sending text data. And then other than that, there's some other kind of vocab or things to know about is memory map. Memory map is basically a single address space. That's part of the unified memory. It's also known as flash, which is ROM, and there's RAM, and then peripheral access using 32-bit address systems. The flash ROM starts at the address 00000. Yeah, basically it holds vectors, codes, uh, read-only RO data. RAM is starts at 2000 and then 0000, and it holds data in the stack, and it goes down rather than up. There's the I/O devices, which start at the 4 thing over here, and it's the peripherals mapped. And inside here, we have some more just things to know about assembler directives. So then some of the common directives are syntax unify, global func, text, thumb func. So basically, these are just essentially instructions to tell the assembler to use modern unified syntax. For a syntax unified, this one makes func visible to other counterparts of the program. So a code from main, texts start the code of start of code section to be placed in ROM, and the thumb func is to use some instruction set. So like each of these have their meaning. So this is sort of what like a very, very simple assembly looks like. We have func, it adds this, and then it adds R0 to R1 and stores it in R0. That's kind of what it does. BXLR does branch exchange to link register, which returns the controller to the caller. And then, yeah, we have seen this before earlier from the first lesson. And then before the full build, we can inspect individual object files, which are in the file.o to see the translation. So some useful instructions we should know is make all. Make all basically is a command that automates the build process to produce .hex file. And then more is the instruction for reading the binary as text. So that's helpful. Hex dump is to print raw binary as numbers. Arm, this long object dump D. Basically what it does is it disassembles the file showing machine code with assembly instructions. So this is kind of helpful for the thing. Yeah. And then more, yeah. Hex dump, pretty helpful. And then there's the D, which is a disassembler. So it's pretty helpful. Like address, yeah, we kind of need to know it. Hex, raw hex doesn't make much sense to us humans. But yeah, we do want to see like the instruction of what it does line by line in assembly. That's kind of what we can go off of. So the building chain of how everything actually gets converted is the following. I drew a diagram of this. It involves compiling, assembling, and then finally linking. So usually what we start is we have our main file, main.c, we have our library.c, our startup.c, and then our add, like whatever our assembly program, add.s. So then our main.c, we use the GCC. Anything in C, we use the GCC to compile it into object files. So .o, everything .o. And then for assembly, we use GAS to get it to add.o. So then we get it to object file as well. And then all of these we get them together into the ELF form. Um, we do LD controlled by. Um, that's what we do. And then finally from ELF to hex, we use object copy to get to hex file. And this hex file is what we can copy into the microbit to actually run instructions. So for assembling, yeah, this is a typical command to do so. Um, Compiling, this is the command to do so. Linking, this is the code to do so. Um, Object copy strips out metadata, so then debug info, symbol names are not part of it anymore. So then before in the ELF, we would have some of the things, but in the hex, that's taken out. Yeah, ELF basically is executable kind of binary data, code, and metadata combined together. Whereas hex is a flash image, which is just the binary data for running this thing. And then some helpful debugging tools in the thing is Minicom, which is a terminal program used to communicate with the microbit. And then the debugger is called GDB. Inside, like when we enter the thing, it'll look something like this. It'll start off with the GDB, kind of looking like a virtual environment. And then it'll just say GDB, and then you can just input stuff here. That's what it looks like. And in GDB, there's some useful things such as layout ASM, which opens a window showing assembly instructions, layout regs, which open window, current values of CPU registers, break, which sets up a breaking point in the subroutine, stopping the execution, and step I executes one instruction and pause again. So that's pretty helpful. And I'll walk through more of the instructions in the actual lab when I go talk about it. And then next, I'll talk about some laws, I guess, just walking through actual code. So there's this Amada's, I don't know how to pronounce it, this person's law, which means that the maximum achievable speed of an optimization is limited by how often the optimized part is used. So this is kind of pretty intuitive, I'd say. And then below is like kind of like the code for multiplication, which demonstrates mm, how we go from C to assembly to I did not write the actual binary thing, but okay, like the hex thing. But the idea is that this is the C code. This code is in C. This is C. I prefer C++. It's kind of similar to C++, but slightly different, I'd say. C is a bit more, uh, I don't know, just C. And then this here is the assembly. So everything here is assembly. Um, so we basically just translated everything exactly, kind of like, okay, we have the unsigned func, which takes in A and B, and then we define X equals A, Y equals B, Z equals 0. While we go into a while loop, while Y is not equal to 0, we decrease Y, and then Z, we increment that, and then we return Z. What this function is that we first define func, So we use moves to initialize R2, which is RZ to be 0. And now we go through a loop. Inside the loop, we first compare if Y is equal to 0, so R1 is equal to 0. If that is the case, then we're done. If it's not the case, then we execute subtracts R1, 1. So then that's Y equals 1 minus 1. And that adds R2, R0 is Z equals 0, Z plus X. And the B loop means that we're going back to the front, back to here again, and then jump to loop. That's the idea. And once this condition is satisfied, we go to done, which is here. And then we just return moves R0, R2. So basically, we move Z to R0, and then we BXL R. So we quit out of this, kind of return this thing to the main thing. So then that's the idea that in our R0, we have our final value, which is RZ from here. So that's how we get our multiplication done in what is it called, assembly. And if we were to write this assembly in terms of hex, yeah, great. Write out the whole thing, yeah. That's basically just using the manual, transcribing that. Pretty straightforward. Okay, moving on. There's actually inside here I have to talk about several things. It's like each instruction run on average takes 1 step, whereas some things like branching can take up to 3. So I'll talk about this in a bit. And basically, we're just counting the cycles, just seeing how efficient our program is in assembly. So even though I said average, like what I mean by average is that actually each instruction actually takes 3 cycles. We have to fetch, we have to then decode, then finally execute. So this is 1, 2, 3 cycles. But because we can run them on parallelly, we have 3 things that we can run on parallel. So on average, that's why I said it's 1 instruction per cycle. So what I mean is that at one stage you can have one thing is being fetched, one thing is being decoded, and one thing is being executed. So it could be 1, 2, and 3 doing it at the same time. So that's why we can inside the instruction while this is being loaded, this could be fetched, and this could be like what is it called? Um, like executed. But basically, the branching thing means that if we are taking the branch, then we jump. So everything we have like what is it called? Fetched and decoded would be useless, and we would have to start all over again. So that means that we kind of just wasted 2 steps, right? So then that's why we have 3. That's why that's the case. And also something to note is that because we have this pipeline of 1, 2, and 3 in parallel, that means that our PC is always ahead from our current instruction that's being executed because yeah, it's 2 steps ahead. It's already fetching something that's 2 steps ahead, 2 memory locations ahead. And each memory location takes up 2 bytes, right? So then in total, the PC is ahead of the execution. Like the program, I wrote something, not execution, by the current place by 4 bytes. Um, I guess it's, yeah, taken 3 branches, yeah. So then memory access loading takes 1 to 2 cycles. Not very certain. Sometimes it takes 1, sometimes it takes 2. It depends, but most often it's 2 cycles. Branch not taken means it's efficient because it's just a normal 1 instruction thing. Branch taken means that there would be a jump, so then there would be wasted. So the average is definitely greater than or equal to 1. So, yeah, here it's like we want to optimize code as always. So we want to bring it from ON to O login, which would be good. So what we want to do is essentially reduce cycles. We realize that what is actually determining the thing as like the A law, I can't remember what the name was, but basically this A law is that whatever's taken the most is what needs to be optimized, right? So then obviously we do want to optimize the loop and obviously remove the branches as few minimum as possible, right? Taken, especially the ones that are taken. So the idea behind here is that when we write the loop, we could first write the checking if it's 0 and then straight jumping. So then it would just straight get it done, right? And then on top of that, for each step, I could, because every time before in my code, I would have to loop every time to check if it's 1 equal to 0. But if it's, I only need to check that at the front, right? So then that's why I would have this in the front so that I save multiple lines of checking. On top of that, another optimization I could do is guess over here. Basically, the idea is that I could move the compares um slightly down, and then what I can do is I did my adds first, then I did subtract, and then I did my compare. And I actually don't need my BEQ then B. I can just use my B and E, which would be sufficient. Like basically branch if not equal. So then that optimizes my BEQ and B, right? So then that saves me the steps because I already updated my flag inside the compare statement. And another thing I could do to optimize my code further is the idea of loop unrolling. This is actually a technique that's used a lot in designing systems. It's the idea that if every loop I have some kind of B statement, then if like it's taken, then it would have taken more steps. So then what I can do is I can just unroll the average of this, of just adds, subtracts, and BEQ done, and then repeat this process is actually much better than the um usual steps because before it would have been nearly three. Now it's barely like on average it would be much less. So um the branch taken would be minimum, whereas the other one would have been a lot more. So this one is actually a pretty good thing because most of these BEQ are never taken until like it satisfies the thing. So that's why we would sometimes do that loop unrolling. But obviously not too much because obviously the marginal benefits of including this BEQ and the whole repeated process is actually minimal when you increase it to some amount. Okay, so that's it for this week.